12 D waves, 12th of December. Defining waves. Simple harmonic motion applies most directly to oscillations of isolated objects, such as a mass attached to a spring or a bob on a string. Waves, on the other hand, are oscillations of extended bodies. For example, water waves are oscillations of a body of water. A wave disturbance is just one way energy can be transmitted between 2 points. A wave stores and carries energy by periodically converting the kinetic energy of particles, in the case of a mechanical wave, into potential energy and back again. The material through which the waves travel is called the medium. An oscillation in the medium is called a disturbance. The disturbance usually begins at one point in the medium and travels from there. If you drop a pebble into a smooth pond, the water immediately around the pebble begins to move up and down, and soon the water at the edge of the pond is oscillating. The disturbance has traveled to the edge of the medium. One thing to notice about a wave is that the disturbance travels. The medium does not move far. A cork floating in the pond, mentioned above, bobs up and down, but stays in the same area as the disturbance caused by the pebble passes by. The disturbance traveled, but the water sporting the cork did not. A wave is complicated. Suppose you tie one end of a rope to a tree and hold the other so that the rope is taut. Then you shake the end of the rope. In this example, the rope is the medium for the wave. How can you describe the wave in the rope? A graph can help. Refer to Figure 12-23. Figure A shows the rope 0.5 seconds after it was shaken. The disturbance has pulled knot 1 down, but it has not yet reached knot 2. Figure B shows the rope 1 second after it was shaken. The disturbance has now passed knot 1 and has dropped knot 2. The shape of the disturbance has not changed, but the wave has moved. The graphs in Figure A and B are called waveform graphs. A waveform graph is essentially a snapshot of the entire wave at an instant in time. Figures C and D show a different way of graphing the wave. Figure C is a graph of knot 1's vertical position versus time. Figure D is the graph for knot 2. These latter graphs are called vibration graphs. Vibration graphs show the position of a single point in the medium over a span of time. 12.13 Types of waves. There are 2 basic kinds of waves. A longitudinal wave is a disturbance that displaces the medium along its line of travel. A spring, for example, vibrates longitudinally when it stretches and compresses along its length. A transverse wave is a disturbance that displaces the medium perpendicular to its line of travel. For example, the wave along a snapped string is a transverse wave. Many waves have both longitudinal and transverse components. Any physical medium can carry a longitudinal wave. Figure 12-24 shows an air-filled tube with a closed end. A hammer strikes one end of the tube, causing it to vibrate. The end of the tube pushes the air molecules next to it, and these in turn push other molecules. This sets up a longitudinal disturbance traveling down the tube. As the wave travels, the air molecules in some regions are forced together, while the molecules in other regions are pushed apart. The regions where the molecules are pushed together have higher density and pressure than the average for the medium and are called compression zones. The regions where the molecules are spread apart have lower density and pressure and are called rarefaction zones. These zones form and move with the wave. A longitudinal wave moves more quickly in a medium whose molecules are closer together, more dense. Therefore, longitudinal waves, such as sound, travel more rapidly through solids than through gases. For this reason, 19th century railroad watchmen used to detect train activity by putting an ear to a railway track and detect approaching trains long before 2 trains could be heard through the air. Water waves are mostly transverse waves, unlike longitudinal waves, cannot pass through a vacuum. Sound waves, solids can transmit all forms of mechanical waves. Physicists, you will learn later in this chapter, that light is a transverse wave that does not need a medium for propagation. Some waves, such as water waves, with both transverse and longitudinal components, is a complex situation. The restoring force on the molecule that has made a force that pushes the molecules to move in the travel in a vertical circle. Some water waves are more complicated than others. 12.14 Periodic waves. If the vibration that causes a wave is periodic, the wave is also periodic. Periodic waves, like those generated by striking a string disturbance, can carry information or energy from one place to another. Waves carry information the same way a chord carries information. For example, if soldiers are told that one whistle means move ahead, while two whistles mean stay put, then when they hear one whistle, they think move ahead. Similarly, at your games, an eyes regard waves as a code. When the cell in your device sends a light from a fire that vibrates 4.3 times 10 to the power of 14 times each second, they report red. Waves also carry energy. For example, tsunamis, huge water waves caused by earthquake shocks, carry an earthquake's energy far from the quake's origin. The 9.2 magnitude earthquake in December 2004 near the Indonesian island of Sumatra produced a series of tsunamis that swept across the Indian Ocean, killing nearly 230,000 people in 11 nations bordering that body of water. The waves traveled as far as Africa and were detectable in the Atlantic Ocean at Africa's Cape of Good Hope. To describe waves, we use some of the same terms that are used to describe harmonic motion. For a transverse wave, the amplitude, A, is the greatest distance the wave displaces a particle from its average position. A longitudinal wave's physical amplitude is usually half the distance between the positions of maximum and minimum densities that it produces. A equals 1/2 times the difference between Y peak and Y trough transverse, or A es igual a la mitad del producto de la diferencia entre X max y X min, y longitudinal. One wavelength, L, is the distance from one peak, or compression zone, to the next, or from one trough, or rarefaction zone, to the next. The wave completes one cycle as it moves through one wavelength. The wave's frequency is the number of cycles a wave completes per unit of time. Each wave that we will study moves at a constant speed called the wave speed, v. This is the speed of the disturbance, not of the medium. For example, suppose a traffic light turns red when a careless driver is not looking. The other cars stop, but this driver continues until he strikes the car in front of him. That car hits the car in front, which hits the next, and soon the car at the front of the line is struck. It may be 1 second from the time the careless driver rams the last car to the time the first car, 20 meters ahead, is struck. The wave has traveled at 20 meters per second equals 20 meters per second, or 72 kilometers per hour. The other cars approximate this speed. For all types of waves, this speed is related to wavelength and frequency. Since wavelength is the number of meters per cycle, and frequency is the number of cycles per second, the product of wavelength and frequency is the number of meters the wave travels per second, the wave speed. In equation form, LF equals V, 12.12, where V is the wave's speed through the medium. By analyzing the units on the left side of equation 12, you can see that the appropriate units for speed appear on the right, f meter per cycle per second, meter per second, versus velocity. Wave speed is a physical property of the medium. If the medium is uniform, lambda and f are inversely proportional. 12.15 Sound waves. Sound waves are an important part of everyday life. Sound waves are longitudinal pressure waves that come from a vibrating body, such as a tuning fork, and are detected by your ears. When you strike a tuning fork, it vibrates, and the vibration alternately compresses and rarefies the air around it. This compression and rarefaction sets up a pressure wave that reaches your eardrum. Your eardrum vibrates in response to the wave and stimulates nerves in your inner ear through a mechanical linkage of tiny bones in your middle ear. Your brain interprets the neural impulses from this vibration as sound. Because sound waves travel by compressing and rarefying their medium, they must have a material medium to travel through. Sound cannot travel through a vacuum. Like other longitudinal waves, sound travels most rapidly through solids and most slowly through gases. Thus, you can hear a sound sooner underwater than in air, and even sooner if your head is in contact with a solid. You may have noticed that you hear sounds originating on your head bones, differently from sounds only a short distance away. For example, If you scratch a pencil with your fingernail, as you hold it a few inches from your ear, you can hardly hear the sound. If you hold the pencil between your teeth as you scratch it, you can hear the sound more clearly. Your solid skull conducts sound much better than the air next to your ear. The sound you hear depends not only on the characteristics of the wave, but also on the characteristics of your hearing. Three basic characteristics, influenced by both the sound wave and your hearing, describe what you hear. Loudness is the interpretation your hearing gives to the intensity of the wave. Sound intensity, IS, is the amount of power transported by the wave per unit area and is measured in watts per square meter, W per square meter. It is proportional to the square of the wave's amplitude. The intensity of the sound does not directly equal perceived loudness. A sound must be 10 times as intense as another in order to be perceived as twice as loud. The least intense sound a human ear can detect is about 10 to the minus 12 watts per square meter. A sound with an intensity of 10 to the negative 11th power watts per square meter seems only twice as loud as the least intense sound. Therefore, scientists have devised a scale of loudness that reflects this characteristic of our hearing. Loudness was originally measured in bells, where an increase of 1 bell doubles the loudness of the sound and increases the sound intensity by a factor of 10. Now scientists measure loudness in tenths of bells, or decibels, dB. A loudness of 10 decibels is barely audible to most people. A sound that is 20 decibels is twice as loud as a 10 decibel sound. A second characteristic of sound is its frequency, which you interpret as pitch, or how high or low the sound is. A sound with high frequency has a high pitch, and a sound with low frequency has a low pitch. A young person can detect sound frequencies from 20 Hz to 20,000 Hz. Some animals can detect sounds of higher and lower frequencies. Dogs, for instance, detect sounds from 15 Hz to 50,000 Hz. And bats and porpoises detect sounds with frequencies as high as 120,000 Hz. Most sounds are actually combinations of waves of several frequencies. The particular combinations of frequencies can cause two sounds with the same pitch and loudness to sound different, thus giving sound a third characteristic, quality. For example, a trumpet playing middle C at 40 decibels sounds much different from an oboe playing middle C at 40 decibels. Actually, each instrument emits multiples of the frequency of middle C, as well as the frequency itself. The frequency of the dominant note is called the fundamental. The multiples of this frequency are called harmonics. Each instrument produces different harmonics. The oboe tends to emit odd harmonics, while the trumpet emits both odd and even harmonics. Thus, the quality of the sounds from the instruments is different, even when their pitch and loudness are the same. The three characteristics of sound, loudness, pitch, and quality, affect the way sound is perceived. Sounds with high pitch tend to seem louder than sounds of low pitch. Also, the loudness of a sound affects its quality. You're less likely to hear the harmonics in a barely audible sound than in a sound that is comfortably loud. Therefore, you cannot fully describe one characteristic of sound without also describing the other characteristics. 12.16 Doppler effect. So far, we have assumed that the observer and the wave source are not moving with respect to each other. Relative motion changes the observer's perception of the waves. Imagine that you are standing beside a long conveyor belt with milk bottles on it. 2 bottles pass you each second. If you begin walking in the direction the bottles are moving, perhaps only 1 bottle will pass you each second. If you turn around and walk toward the source of the bottles, 3 bottles may pass you each second. The bottles are coming from the source at a constant rate, but the frequency of the bottles passing you depends on the relative velocity of you and the source of bottles. Similarly, the perceived frequency of any sound waves depends on the relative velocity of the observer and the sound source. This is called the Doppler effect. The Doppler effect is responsible for the change in frequency that you hear as a car approaches, passes, and moves away from you. As the car approaches, you will hear a higher pitch than you would hear if there were no relative motion. As the car moves away, the pitch will drop to a lower than normal pitch. When the car, the source of the sound waves, is moving toward you, the crests of the waves are hitting your ear more frequently. This is perceived as a higher pitch. When the source of the sound waves is moving away from you, the crests of the waves hit your ear less frequently, and this is perceived as a lower pitch. Notice that this is a relative phenomenon. The actual sound emitted by the car does not change. We are so used to this phenomenon that we form an impression of how fast a car is going by the degree of the Doppler effect as it drives by. 12.17 Modeling Mach Speed. As with any wave, the speed of sound is a function of the medium through which it travels. The density of the medium is one factor that controls the speed of sound through the medium. The density of a fluid depends on its composition, its pressure, and its temperature. Interestingly, with the atmosphere, only its composition and temperature seem to significantly affect the speed of sound through it, since both temperature and composition of air change with altitude. The speed of sound in air also changes with altitude. Examine the data table below relating Mach speed, air temperature, air density, and altitude. Mach 1 is the speed of sound at a given altitude, temperature, and density.